Okay. And it's also assumed that you have capacitive loads. I will try it to VDD, but it can be a combination of VDD and ground and probably other nodes as well. This is the differential latch that we have, right? So, what is the effect of the width of M3, M4, M5, M6, also M1, M2, or they don't have any effect and we can just size them whatever we want. Your friend said the exact opposite, so you can argue with him. No, you said M3 and M4 affect the whole time. He said M5 and M6 affect the whole time. Oh, you also said M3 and M4. Why? Okay. Okay. So, someone give me the definition of setup time and hold time. Maybe I have it backwards. So, let's say the data input is here. The clock does this. I have clock here. So this is the sample phase. Sample meaning detect the input, and this is the hold phase. Okay. Now, the idea is that the data can change anywhere in this interval, and at the end, during the hold phase, the value at this point during the negative edge of the clock will be held. That's what we want. Okay. So let's say the data. So where is the hold time? Where is the setup time on this diagram? What is the hold time? Okay. So let's say the data changes here. Okay. The data changes at this instant. I have drawn the differential one where they cross each other is where the data changes sign. And then of course they can cross again. But this change in polarity of data here is not supposed to affect the output. Okay, what is the hold time? Is this the hold time? When the clock is high? What is the hold time? After the clock becomes low or high? No, here, see, when the clock is high, the input is directly affecting the output. And when clock is low, that is the hold phase. Okay, so where is the hold time? After the clock becomes low. So the amount of time for which data has to be held constant after the clock becomes low. Is that the whole time or not? That is right. Okay. And what is the setup time? Before the clock rises. Why rises? See, these things relate to the sampling ability of the flip-flop. Okay. It's not a flip-flop, it's a latch. If it's an ideal latch, the data can change anywhere it wants. As long as it is stable right at the location of the clock edge, it will sample that value and then hold it. Okay, any of the other transitions don't matter at all. In reality, they do. So if the data changes before the clock edge but very close to it, then the latch may not be able to hold the data. Similarly, if the data changes immediately after the clock edge, it may not be able to retain the data. Although it is technically in the hold phase, it may not be able to retain the data. One thing to observe is that it takes a finite amount of time even for the clock, the lower differential pairs to switch. Okay, because of finite rise time and the finite on voltage of the differential pair. Finite switching voltage of non-zero switching voltage of the differential pair. Okay. So why do we have this setup and hold times? So now explain to me which pair affects what? M3 and M4 and M5 and M6. Let's imagine that the clock, this M1, M2 switch instantaneously, okay? Just for sake of argument. Now what is the effect of M3, M4 or M5, M6? Why? Because it was opposite to all the answers that were given so far. Yeah. Setup time is larger if M3, M4 is stronger or weaker? Yeah, in a way that is right. So see, the system we have is something like this. We can think of it as a transconductor. This is just a linear model of it, and this is driving an RC load. This is what we have when clock is positive. Effectively, this is the system that we have. And when the clock is negative, this is what we have. Okay, this is a GM. Now, in this case, during clock, if the data changes at some point, so let's say the data is somewhat small amplitude and it changes here, then the output at this point will respond to it depending on the time constant RC. Okay. So even if this changes instantaneously, the output will take some time to respond. It will, let's say I'll show the delay as being a little bit exaggerated. So this is a little messy diagram, but let me draw single-ended diagrams for this. During clock phase, let's say D changes like this as a step, and Q, if it's a first order system, will do something of this sort. Okay. And what happens in the clock bar phase? So let's say the latch goes into clock bar phase at this point. Then this will be the initial condition for the second circuit, and it will regenerate from there. Okay. Now, as you bring the step closer and closer to the clock edge, this is what? The initial condition gets smaller and smaller for the regeneration phase. So, it may not regenerate. So, what does it affect? It affects the setup time. So, there is a minimum amount of time before the clock falls negative, for which, during which the data should not change. If it changes, the output also tends to change, but it may not change completely. Okay. Actually, the way I have shown it is also not right. The data should change from negative to positive values. In fact, if it does that, it may stay in the negative region. Okay. The initial condition may be negative. In fact, in that case, instead of blowing up in this direction, it will blow up in the opposite direction. So, you won't be able to latch the data if the data changes too close to the clock edge. Is this clear? Then in this phase, you set up the initial condition for the regeneration phase. So, the initial condition for the regeneration phase should have the same polarity of the data that you want to latch. But if the data changes polarity too close to when it enters regeneration phase, the initial condition will not have the right polarity, or it may have the right polarity but not enough magnitude to regenerate. Okay. In fact, let me clean this diagram a little bit. So, the D changes from negative to positive here, and Q, depending on the time constant, it will change from, it will tend to do this, and then starting from this point, it is supposed to blow up and regenerate. Okay. Now, if we have it even closer, it will tend to do this, but then from this point on, it will regenerate in the opposite direction. Okay. Although, if you look at the clock edge, the input data is positive, you have latched a negative value. Is this clear? So, how can you reduce the setup time? So, if you make this GM stronger and stronger during the sampling phase, then what happens? This slope we said was GM by C, right? The starting slope of this. So, it will tend to go faster and faster. So, maybe not with this. Let me make another diagram for this. So, maybe the D, when the D does this, the Q output is supposed to, will do something like this, and as you increase the GM, it will do this. Okay. So, let's say if the clock edge was here, it would not be able to latch the first case, but it will be able to latch the second case. Right. The first case will regenerate and go in this direction, the second case will regenerate and go in this direction. So, by increasing the first GM, you can reduce the setup time. Of course, there is a limit, because you are not simply increasing the GM when you increase the width of the transistor, you are also increasing the load capacitance. So, at some point it stops working, and also you are increasing the load presented to the previous stage. So, that may increase the rise time of what is driving the D inputs. If you assume a constant rise time for the D input, all this happens. But if because you increase the loading to the previous stage, if the previous stage is not working properly, or maybe the previous stage is slowed down too much, then again this won't work. But if you have to improve the setup time, this is the route that you have to take. And of course, like with any circuit, you will reach a point where the transistor's own parasitic capacitance will dominate the picture. So, at that point, you can't do anything. Given a transistor, its GM to capacitance and all of this is fixed, right? You can't change the performance beyond that. That is the technological limit. Like one measure of technological limit is FT, right? The transit frequency of the transistor. So, that is the ratio of the transconductance to the capacitance of the transistor itself. So, if a transistor was loading another transistor, that would be the unity gain frequency. So, similarly, you will reach maybe not the same frequency, but something related to FT, because the transistor will start loading itself. Okay, now what's the effect of M5 and M6? Does it have any effect at all? Yeah, that's true. Of course, GMR should be greater than 1. But once it's greater than 1, does it matter whether it is some particular value or something else? Okay. So you are saying you should use the smallest transistor. Okay, GMR is 1.01. Yeah. So where is where would you size it? Okay. So let's say we design it. We have designed the latch so that it regenerates within the half clock cycle that we want. Is there any point to increasing the size of M5 and M6? Do any of the parameters of the flip-flop get affected or no? Huh? Rise time and fall time on the output will be affected. Okay, that's true. What are the parameters of the flip-flop again? So we have the clock, okay, and the data can change before and after. This is the D input. This is the setup time. This is the hold time. And also if you look at the Q output, it appears a little bit after the clock. So maybe it is positive up to here and negative. And this is known as what? This is the clock to Q delay. Okay. Does the size of M5 and M6 affect any of these things? Why? Yeah, that may happen. Okay. What else? Does it really affect the clock to Q delay? What about hold time? How do you adjust the hold time? Or is there no freedom to do that? What is the hold time? 0. What is the definition of hold time? Yeah, so why would you want to do that? I mean, what aspect of the circuit makes you have to keep the input constant for a period after the clock edge? Huh? Does it differ? Is that the hold time? I mean, because hold time seems to be after the clock has changed polarity, right? So the initial condition for the latch is reached in the sampling phase, not within the hold time, because you have half a clock cycle to regenerate. You don't need the exactly. Why would that change? Why might that change? That is correct. That is the reason. But why might that change in the hold phase of the? Yeah, it takes time for the current to steer from one side to the other. Okay. Firstly, the rise time of the clock will be finite, and the switching voltage of the differential pair is also non-zero. Okay. I keep saying finite when I should say non-zero. So both the rise time and the switching voltage are not zero, right? So if you look at the system, previously I drew it as though only one of these transconductors is active in the whole sample phase and another one in the hold phase, but that's not true. This is the circuit, and for a period both of these will be active, and essentially the GM of this goes from the maximum value to 0 and the GM of this goes from 0 to maximum as you switch the clock from sample to hold phase, right? So basically this differential pair turns off and this turns on. That's what I'm saying, but it takes some time. So the current that is being pushed into this node, the RC parallel combination, will be a linear combination of this VD, the input voltage that's applied, and the output voltage that is present, VQ. Okay. So it is not just a function of VQ. What you would like is, during the sampling phase, this voltage depends on VD, and during the hold phase, it depends only on VQ. Okay. So it samples and then regenerates, but that doesn't happen. So as you switch the clock, even after the clock has crossed this point where cross the 0, there is some current flowing through the input differential pair. So the input will contribute to the output. So if it changes polarity, and if the initial condition was small, it could be that it will flip the logic, it will flip the polarity of that, and regeneration starts again. Regeneration is going on. It will go on after this completely switches off. If the polarity of this has accidentally turned around, then it will latch the wrong value. Okay. Clock and clock bar. What happens? What is the if there is a okay. Yeah. Really? What determines whether the clock pair is switched on or not? What determines the switching of the clock pair? Which voltage? I mean, which voltage in the circuit determines the clock? I'll discuss this. So the problem I was discussing with the hold was, as the clock changes polarity, this is supposed to be the, let me exaggerate its time somehow. So let's say this is the clock. So this is supposed to be the sampling phase and this is the hold phase. But during this transition, both differential pairs are active. Okay. So let's say the input changes from negative to positive just before the clock and then back to negative. Okay. That is kind of the worst case for latching. Then the Q, it was at negative, maybe it reached a small positive value, but here it reaches negative, okay, but during this time the input differential pair is still active. So if the input is large and negative, this can take it to the other direction, okay. So it was supposed to regenerate from here and reach this value, but it will regenerate somewhere from here and reach the opposite value. So you need to hold the input constant for a period beyond the clock edge. Essentially the current going into this R and C, if you take the linear model, will be Gm times Vq plus Gm, let me call this the hold. So Gm of the differential pair 5, 6 times Vq plus Gm of differential pair 3, 4 times Vd. And this equals C times Vq dot plus Vq by R. Okay. So the solution to this differential equation is what you get. Of course, this is valid only when everything is operating in small signal linear region, but it gives you an idea. So because it depends on Vd, if Vd turned to be a small positive value and went back to a large negative value, it can flip the initial condition on the regeneration. Okay. Is this clear? And how does the size of 5, 6 influence the whole time? GM5, GM6, do they have any influence or not? Yeah. Whole time would be smaller. See, during this period, this part is trying to regenerate the voltage, whereas this is trying to take it in the opposite direction. Perhaps it is taking it in the direction of the data. If the data remains the same, there is no problem. The problem is if the data switches sign. So if the part that is regenerating is stronger than the part that is driven by data, you will get a smaller hold time. Okay. So you can reduce the hold time by increasing the size of M5 and M6. You can reduce the setup time by increasing the size of M3 and M4. No, this is what happens. You have to hold the data for longer, that's all. See, you make a flip-flop assuming that you capture the value of the data on the edge of the clock. Now we already said it can't be the edge, it has to have some period. So your sampling, it's not the sampling uncertainty, but your data cannot change very fast. And that's what happens. Okay. Ultimately, it will limit the maximum speed that you can operate at. Finally, what affects the clock to Q delay? Clock to Q delay is the delay between the clock crossing 0 and the output data flipping sign. Huh? GM5 and C. Why GM5? No, I know, but why that? It will actually depend on M1 and M2 because, see, if M1 and M2 don't flip the sign of the output data, it will never regenerate to the opposite direction. So it's the size of M1 and M2, M3 and M4. I think we call that M3 and M4. That matters. So this is M3 and M4. So let's say we keep the lower pair fixed. This is M3 and M4. Now, when you apply the clock, it is this that drives the data in the opposite direction, okay? And that is determined by the size of M3 and M4. So the zero crossing of the output data is determined by M3 and M4. And of course, M1 and M2 also matter because the clock, if the lower pair switches very slowly, then there is a delay in the output switching also. Okay. So it's mainly these transistors that contribute to the clock to hold time. The clock to Q time. Okay. Yeah, that's correct. All I'm saying, see, there are different measures of this, right? Because it's not really a ramp or something. So I'm taking the difference between the clock crossing 0 and Q crossing 0. The Q cannot cross 0 because of regeneration. Regeneration will only take the existing polarity and blow it up to a large amplitude. Okay. So if you look at the zero crossing point, the M5 and M6 don't affect it. What M5 and M6 do affect it is whether it comes out like this or like this. Size of M1 and M2 will affect, yeah, actually everything affects everything in that way. Yeah, that's true. Size of M1 and M, if you make M1 and like M1 and M2 are crucial to everything, right? If they don't switch at all completely, then the input is always contributing to the output and the positive feedback latch is always active to some extent. So M1 and M2 will contribute to everything. So you have to make M1 and M2 faster for it to switch from one phase to another, and M3 and M4 and M5 and M6 affect them in individual phases. But again, if you make M1 and M2 larger and larger, they will switch faster. That is, they will switch with a small threshold voltage. But the problem is that it will increase the loading on the previous stage. Okay. Any questions? Did everyone understand this discussion of how each of these affects the parameters of the flip-flop? It is a kind of qualitative discussion, but you can get a quantitative idea by estimating the GM of each of these pairs. But also you should keep in mind that it's heavily nonlinear, right? Once the differential voltage goes beyond a few tens of millivolts, the effect is nonlinear. The differential pair becomes nonlinear. So you have to also use simulation, but you can use these, use these guidelines to go in the right direction while optimizing the flip-flop. And sometimes, I mean, you do need to do this because you always generally start off with equal size differential pairs for the latching and the sampling M3, M4 and M5, M6. But sometimes you may have to optimize the setup time or sometimes the hold time depending on the kind of data that you expect to see. So in that case, you make one or the other bigger. Anything else? Any questions on any aspect of the latch? So at this point, we'll stop discussion of this transistor level digital blocks. I had originally planned to do the signal processing part first and then the circuits afterwards. But then I realized if I do that, then we'll have to spend most of the semester not actually designing transistor level circuits. So I flipped the order. So this way you can start with transistor level circuits and also use that in whatever signal processing that we have to do. So you were asking about having overlap in the clock, right? What he was referring to was, if clock and clock bar have waveforms like this, I imagine them to have waveforms of this sort where this is the common mode of the clock. Okay. I say clock and clock bar, again, I don't mean that the logic levels are 0 and VDD. They are the appropriate values needed for switching. Okay. You are talking about cases that are like this or like this. Okay. So what happens if you do that? Okay. Okay. So you are saying you are getting rid of this whole time problem, right? Is that correct? He has proposed a solution to this whole time problem. You arrange the clocks like this. Clock and clock bar have a negative overlap. Now the claim is that during this period it is sampling and then both are off, and during this period it's holding. So there is no instant of time during which both M3, M4 and M5, M6 are affecting the output, so there is no hold time problem. Is that the claim? What do you think? Does it work like that? No, let's say that's not the case. Okay. Let's say it's able to hold it for that much period. No, they both are off because then there is no instant of time during which both differential pairs are affecting the output. That's the bottom line, right? So I had written this GM56 VQ plus GM34 VD. What he is saying is this will never happen. Okay, it's either the first term or the second term. Is this correct? It is correct. Okay. Yeah. So what happens? It's always non-operative. No, that's not right. I mean, like, what's the difference here? Here, this seems to be the same as this one. So why do you say it is non-operative? Pardon? What is a positive latch? Actually, is there an instant of time where both the differential pairs are off? What determines whether M1 is on or M2 is on? Yeah, the difference between clock and clock bar voltages. So what happens here? In case 1, clock is no, here it is not, right? In this part. Oh, case 1, okay. No, this is clock and this is clock bar. Not like this, okay. See, it's actually not that the differential pair is turned on by the difference voltage, not by the individual voltages. So, if you plot the currents in the, let me call the 0th case, and plot the current through M1 and M2, it will be 0, one of them will be 0, other one will fall to 0, okay. So, that is the current through M1 and M2, and if I plot it for case 1, what happens? It will do something like this. So, during this phase, both M1 and M2 will be on and carrying half the current. The one, I am assuming right now that this is an ideal current source, or this voltage is large enough that the current sink is not affected, okay. Now, the current sink will be affected. What happens is, when clock and clock bar both go to 0, this voltage experiences a dip. In fact, it experiences a dip in all cases, but in this case, it experiences a large dip. So, that will affect the current source to some extent, but it's not true that one differential pair, both differential pairs are off. Both will be on to equal extent. In fact, the problem is compounded if you do this. Is this clear? Yeah, that's why both, this is carrying half the current, this is carrying half the current, both are active. What you want to do for switching is to minimize the period during which both are simultaneously active. And that you can do by a waveform like this. Why? What is this? If differential pair input voltage is 0, both will be off. How come? They will have equal currents, right? So, in fact, this extends the period for which you have both will be on. So, this can worsen the problem. So, what happens in reality is this voltage will dip down. So, this current magnitude reduces, but still both will be active. Okay, maybe they are not as strong. So, it will actually make it slower and a little bit worse if you try to do that. Yeah, that's correct. So, I didn't talk about sensitivity. Sensitivity is the smallest amplitude that you can apply to D and D bar when the latch operates correctly. So that, meaning, I say the input is digital. In this case, we will talk about many cases later where the input is smaller than the full logic level, okay, and the D flip-flop is supposed to restore it. The smallest amplitude it can sense depends on M3 and M4. It should take the smallest amplitude, differential amplitude, create the right initial condition at the output so that the output regenerates to the right value, okay. So, for that, you need to have sufficiently strong M3 and M4. I think we discussed it yesterday, right? So, we know how to tweak the sensitivity, setup and hold times, and probably the clock to Q delay of the latch as well, right. Of course, you may not have freedom to optimize everything, but if you want one of them skewed in favor of the other, then you can modify one of these things, right. And also, if you get a certain setup and hold time, you should be able to identify the cause for the limitation, okay. Let's say you can't go beyond a certain setup time, 10 picoseconds. Why not? So, that will impose a limitation on the speed, right. So, you should be able to figure out why that's the case. Anything else? Any questions or discussion on whatever we have discussed so far? Okay, then we can stop.